Imagine it is 4:30 in the morning and your house wakes up before you do. Not because it has detected motion, because it has read the weather forecast, checked the battery, watched the greenhouse cool through the night, and noticed that the well pump is drawing a little more power than usual. It has a plan for the day. Clouds are expected after lunch, so it delays the water heater. It moves the greenhouse irrigation to the sunny part of the morning. It keeps a larger battery reserve because the forecast is uncertain. And when you finally walk into the kitchen, you can ask one simple question. What should I know? The answer does not come from a data center. It comes from a small computer in the house. Could a local large language model actually run an off-grid homestead? Welcome to AutoIntellect, a podcast about making artificial intelligence more practical, more independent, and more grounded in the physical world. I'm your host, and for our first episode, we are building an AI brain for an off-grid home. Not a science fiction brain, not a chatbot with a dashboard. A system that could help manage solar power, batteries, water, food production, appliances, maintenance, and voice control when the internet is unreliable or completely gone. The short answer is yes, with an important qualification. The language model should not be the thing keeping your pipes from freezing. It should be the layer that understands, explains, and coordinates a collection of simpler, testable systems. That distinction is the whole design. An off-grid home is an unusually good test for useful AI because every resource has a budget. On the grid, you can often ignore timing, flip a switch, and power arrives. Off-grid, a 2-kilowatt appliance is not merely on. It is on while the battery is at 40%, the sky is overcast, the pump may start, and tomorrow's solar production is uncertain. Water has the same character. A tank level is not just a number. It connects to rainfall, well recovery, irrigation, leaks, filters, and the energy required to move every gallon. Then there is the greenhouse. Temperature, humidity, soil moisture, vents, fans, pumps, and frost risk all interact. Add ordinary house loads, equipment wear, and a weak internet connection, and the homestead becomes a small, living infrastructure problem. Today, these systems are usually separate. The inverter has one interface. Water sensors have another. Greenhouse automation follows fixed rules. Maintenance lives in a notebook or in someone's memory. The opportunity for a local model is not to replace those systems. It is to give them a common language. Open-source tools already provide much of the foundation. Home Assistant can run locally, connect to energy monitors, solar inverters, batteries, water meters, and individual devices. Its local voice pipeline can use on-device speech recognition and speech synthesis, so spoken commands do not have to leave the property. OpenEMS takes a more specialized approach to local energy management, integrating storage, renewable generation, chargers, heat pumps, and other equipment. And the research is moving from dashboards toward agents. Recent home energy experiments divide the job among specialist agents for analysis, knowledge, and control. Another open-source system uses an orchestrator and specialist agents to translate natural language requests into multi-appliance schedules. That does not mean the problem is solved. It means the pieces are becoming recognizable. So, what would we actually build? I would divide the homestead brain into 5 layers. Layer 1 is observation, sensors and meters. Solar output, battery state of charge, inverter load, tank level, well pump runtime, water pressure, greenhouse temperature and humidity, soil moisture, freezer temperature, generator fuel, smart plugs on large appliances, maybe vibration and current sensors on pumps and fans. This layer must work without an LLM. It should record reliable time series data locally and make sensor failures obvious. If the water tank reports 62% for 3 weeks without changing, the system should suspect the sensor, not celebrate perfect stability. Layer 2 is forecasting. Start modestly. Estimate tomorrow's solar production from the weather forecast, season, panel geometry, and recent performance. Estimate the house's baseline load from its history. Predict likely water demand from irrigation schedules and past use. None of this requires a giant model. Classical forecasting, simple regression, or a small time series model may be faster and easier to verify. The forecast should include uncertainty. We expect 12 kilowatt hours sounds precise. There is a 70% chance of producing between 9 and 14, is much more useful when a cloudy day could empty the battery. Layer 3 is scheduling. This is where the home decides when flexible jobs should run: laundry, water heating, irrigation, battery charging, tool batteries, food dehydration, or pumping water uphill into storage. Again, the LLM should not improvise the schedule one appliance at a time. A small optimizer can consider power limits, deadlines, battery reserve, expected solar, and equipment constraints all at once. The model translates human preferences into those constraints. You say, "I need clean clothes by 6, protect the freezer, and save enough power for tonight." The model turns that into a deadline, a priority, and a minimum reserve. The optimizer produces a feasible plan. Layer 4 is execution and safety. This is the unglamorous layer, which means it is the most important. Every physical action passes through deterministic rules. The pump cannot run dry. The battery cannot cross its protected reserve. The greenhouse heater cannot overload the inverter. A voice request cannot disable a freeze alarm. Critical controls continue operating if the model crashes, hallucinates, or takes 30 seconds to answer. Think of the LLM as a chief of staff, not the circuit breaker. The execution layer should also use permissions. Reading the battery is easy. Moving a load within an approved time window may be automatic. Starting a generator, opening a water valve, or changing a frost protection setting should require explicit confirmation, or be unavailable to the model entirely. And every action gets an audit trail: what changed, why it changed, which constraint allowed it, and how to undo it. Finally, Layer 5 is conversation. This is where a local LLM earns its place. It can answer questions that are awkward to encode in a dashboard. Can I run the washing machine? Why did irrigation move to 10? What changed since yesterday? If the clouds arrive early, what do we give up first? The model can retrieve current sensor readings, the day's schedule, equipment manuals, and maintenance records. It can explain the optimizer's result in ordinary language. It can also admit that it does not know. For routine commands, a narrow local voice system may be better than an LLM: fast, predictable, and able to run on small hardware. The model is most valuable for questions that require context, trade-offs, or explanation. Let's run one day through the system. At dawn, the battery is at 38%. The overnight baseload was slightly higher than expected because the greenhouse fan ran longer. The solar forecast says the morning will be clear, followed by a thick cloud layer at 1:30. The house has 4 flexible jobs: heat water, run irrigation, wash clothes, and charge a tool battery. The scheduler places irrigation first, but not immediately. It waits until the panels have covered the house load and the battery has begun charging. Water heating follows near peak sun because its load is large but interruptible. Laundry gets a start window before noon. The tool battery is low priority and moves to tomorrow if the solar forecast weakens. At 9:15, the well pump starts. Its power draw is 12% above its normal range. That is not enough to declare a failure. The system checks water pressure and pump duration. Pressure is slightly lower and the pump is running longer for the same tank increase. Now it creates a maintenance note: inspect the intake, filter, and pump before the trend becomes an emergency. At 11, you ask, "Can I use the table saw for half an hour?" The assistant does not merely look at the battery percentage. It simulates the extra load against the current plan. The answer might be, yes, if you start before noon, we can keep the evening reserve by pausing the water heater. I'll resume it if solar production stays above forecast. Should I make that change? That is a genuinely useful interaction. The system is not saying yes or no in isolation. It is offering a trade. At 1:10, clouds arrive early. The solar forecast updates. The optimizer runs again, preserves the freezer and evening reserve, and drops the tool battery from the plan. Irrigation has already finished. The water heater has enough stored heat. Nothing dramatic happens. Good infrastructure should often feel boring. What hardware would this require? The control system and the language model do not need to live on the same machine. A small, efficient home automation computer can run sensors, rules, dashboards, and the local database. A separate mini PC can host the local model, retrieval, and heavier forecasting. If that machine is asleep or unavailable, essential automation continues. Model size depends on the job. You do not need the largest model you can fit. A smaller, quantized model with reliable tool calling, constrained outputs, and good retrieval may be more valuable than a much larger model consuming scarce power. That power cost should be visible. If an AI assistant burns a meaningful share of the energy it is trying to save, the design has failed a basic test. Run heavy summaries or forecast updates during solar surplus. Let the model sleep. Use rules and small models for common commands. Wake the language model for the questions that actually need it. Limited connectivity also changes the software philosophy. The home should cache weather forecasts, manuals, maps, and system documentation. It should continue using a conservative fallback forecast when the internet disappears. Updates should be deliberate, with a known good version to roll back to. The local network should be enough to operate the property. Privacy is a benefit, but resilience is the deeper point. Local voice recordings can stay local. Detailed occupancy and energy patterns do not need to become a cloud services dataset. More importantly, the system remains understandable and useful during an outage, the exact moment when the homestead needs it most. There are real failure modes. Sensors drift, forecasts miss, smart plugs disconnect, models invent explanations. An optimizer can satisfy the constraints you wrote while violating the intention you forgot to write down. So the design needs graceful degradation. When confidence falls, the system becomes more conservative. When data is missing, it says which data is missing. When the model and the safety controller disagree, the controller wins. When the network vanishes, the home follows a local reserve policy. Manual switches still work. The research gives us reason for optimism and caution. Multi-agent energy assistants have reported strong results in experimental evaluations, including high goal achievement rates. Agentic load schedulers can approach mathematical optimization benchmarks in some test scenarios, but other building energy experiments show that performance varies sharply by task, with difficult cost estimation and scheduling questions still exposing weaknesses. And almost all of these demonstrations live in cleaner environments than an actual homestead in winter. The hard part is not producing a plausible sentence. The hard part is sensing the world accurately, expressing priorities as constraints, verifying actions, and recovering safely. That is why the most credible version of an AI homestead is hybrid. Machine learning predicts, optimization schedules, rules protect. The language model connects those pieces to a human being. So could a local LLM run an off-grid homestead? Not alone, and that is the wrong goal. But could it become the interface to a local, resilient operating system for the home? Could it notice patterns across power, water, food production, and maintenance? Could it turn "keep us comfortable through Friday's storm" into a plan, explain the compromises, and ask before making consequential changes? Yes. The open source foundations already exist. The models can run locally. The sensors are affordable. The optimization problems are understandable. What is missing is careful integration and a lot of testing in the messy real world. This thought experiment could become a project. First, a read-only assistant, then forecasts, then advisory schedules, and only much later, limited control behind hard safety boundaries. That progression matters. Trust should be earned one layer at a time. This is AutoIntellect. If you want to follow this idea, we can make it a recurring series. Choosing hardware, designing the data model, testing solar forecasts, building a battery scheduler, and eventually putting a local voice assistant in the loop. For now, here's the question I want to leave you with. If your home could explain how it was using power, water, and time, what would you ask it first? Thanks for listening.